Hey guys, welcome to the second radical video. So this one is going to be focusing on another kind of radical reaction. But before we go on to that, I'm just going to talk about the last video really quickly. So if you remember, we used HBr with some sort of peroxides, and the Br added to the last substituted carbon of the double bond. So I'm just going to quickly talk about why that happened. So we had this reaction, HBr, peroxides, and we at one point formed a Br here and a radical over there, right? So why do we form that instead of, that was incorrect. So why do we form a radical over there instead of like this and the Br over here, right? So the reason we formed it on that secondary carbon is because radicals follow the same rules as carbocations in terms of stability. So like secondary would be more stable than primary. So that's why we formed it in the secondary. Okay, so for looking at the stability, that primary radical would be less stable than the secondary radical, which is less stable than the tertiary radical. Okay, and also radicals, like carbocations, were stabilized by resonance, so radicals have this very similar effect. So we have something like this, and a radical right there. We have two electrons in that bond. So one of them can break off and form a bond with that radical, and this one will go onto that carbon. And so we would get something like that looks like that. Okay, and so yeah, that just always watch out for the stability. And so now we're going to look at another kind of radical reaction here. So before we looked at HBr with peroxides. Now I forgot if I mentioned it in the last video, but HBr and peroxides is the only one of the halogens that work. If you do HCl or HI, it doesn't work with peroxides, so you have to use HBr. Okay. So now what we're going to talk about is this radical reaction, Br2, with something like light or heat. So light, you can be written as HV, just in case you see it on a test that way. And what the difference here is that it works with alkanes, not alkenes. All right. And so the initiation step is actually a little bit simpler than our first reaction. So we have a Br. There's two electrons in here. So we break up that bond first, right? Two electrons in the bond. We took one electron and added it to each bromine. We have two of these Br radicals, right? And so if you remember in our initiation from the previous reaction, we had to break up the peroxide into radicals, and then we reacted with HBr to form our Br radical. So that was two steps. So this is a little bit simpler in that we only have one step. So that's our initiation step. Now with the propagation step, we take an alkane. I just drew this one similar to our original example, except no double bond. And we reacted with our Br radical. And so what we're going to do is we're going to form the most stable radical. So to do that, let's identify our most stable carbon here. That would be this tertiary carbon. All right, same rules as carbocations. And so what we do is we take a hydrogen from there, and that's going to react with our radical. We have to break that hydrogen-carbon bond, this one right here with the two electrons. So one of the electrons is going to form a bond with the Br. The other one is going to end at that carbon that it was part of originally. And so to help you guys visualize it better, take that red electron. It's going to reach out and form this bond there, and then the Br electron, the Br radical, will reach out and help connect it. Okay, so we have this continuous little bond, and so we're going to form HBr. And now we're also going to form a radical because we took this one electron and we put it right on that carbon. And so we're going to have a radical on the tertiary spot. Okay. Then what happens is we take another one of our Br2, right? And we're going to react it with the radical. So there's two electrons here, right? So this electron is going to reach out, that radical reaches out, and one of the radicals here, one of the electrons forms a bond. The second electron goes on that Br, and so let's try to visualize it better. Take that radical, help form kind of half of the bond you can think of, and then we take one of these electrons, and it forms the other half. So it connects the Br to that radical. So we're going to put a Br on that tertiary carbon, and we form another Br radical. And so that Br radical can go on and react with another one of our alkanes, and the reaction goes on and on. And so what you can see we did is we replaced the a hydrogen on the most stable carbon with a Br. Okay, and so let's try a little bit of a more complex example. So if I gave you guys this structure here, right, reacting with Br2 over light. Okay, your whole goal is to put a Br on the more stable carbon, right? And remember, radicals follow carbocation stability rules, right? So remember, carbocation can resonate. They prefer more substituted carbons. Same thing applies here. So our job is to find the most stable spot, right? So let's look. What immediately jumps out? Well, we have a tertiary here, right? So that would be a good place to consider. But we also have maybe this carbon here. Why? Because it's next to a double bond, right? And so if we did end up forming a radical there, it can kind of resonate in a way, right? And we can shift that radical around, stabilizing it better. But there's actually another more stable spot, and that would be this carbon right over there, right? Now, why would it be that carbon? Let's go through our mechanism. The initiation step is the Br breaking up. So we're gonna draw these fishhook arrows, getting to these Br radicals. That's our initiation. And then our propagation step. Just gonna erase these. And so we have one of the Br radicals. And what it does is it takes a hydrogen off the most stable spot. So let's look at this hydrogen. Let me just move this. And so that radical forms part of the bond. The other one is going to come from that carbon-hydrogen bond. And then that one breaks off onto the carbon. And so at one point, we'll have this little radical intermediate. Right, we're going to have, so let's see, that carbon. And so we're going to have a radical right there in HBr. So why would that radical be the most stable? It looks like it's on a secondary carbon when we had a tertiary over here. Well, if you look, we have two double bonds right next to it. So we can stabilize this radical by going like this. One of those electrons breaks off here, right? Because remember we have two. And then that radical is going to also form a bond. And we can get this structure. So we have this double bond still here. Now we have this, and we're forming, oh wait, and I messed up one of the arrows here. That radical breaks. Right, sorry about that. And we have a radical there, right? But we can also do it with that other double bond. And so now we can do it this way. One of the electrons gonna form part of the bond. Our radical forms the other. And then this radical breaks onto that carbon. So our product here would look like this. So we're gonna have this double bond stays. We're gonna form a bond here and a radical there. Right? So you can see that we can essentially move this radical over a pretty good distance of carbons, right? We can have it right here, or there, or there. So we can think of it almost as resonating the carbocation, the more the better. Any other spot, like let's say right here, will only move the radical to this carbon, one over, right? Same thing with this spot, it'll just if we form the radical there, we form a carbocation, a radical right there. And the tertiary has no, I guess, resonance stabilization, you can think of it. And so we would prefer to form our radical right there, on in between the double bonds. Right, so we have a radical, we have another Br, and so our radical is going to form part of the bond. The Br bond breaks, and we get this. Let's delete that. So we're going to keep this here, keep that, and we put a Br there, right? And we have another Br radical. And so that would be our answer for that question if it asks for the major product, right? Just in between those double bonds, okay? So watch out, remember, because they follow carbocation stability rules, you never want to form a radical on a double bond like this, on a carbon part of a double bond. Not a good thing to do. And so that was with Br2, that reaction. So you may see it with Cl2, right? Instead of Br2. The thing about Cl2 is it's not as selective as Br2. Br2 added to the more substituted carbon, the most stable carbon that a radical can form on. Cl2 is much less selective, so it can add almost all over the place. And so that will be a separate video, not in this video. And you've seen it in your workshop when it asked you how many different structures you can make with by using chlorine radicals, okay? And so you can make more than just the more stable radical. And so that will be covered in another video. If something here didn't make sense, please feel free to email me. I'd always be happy to help you guys. And also definitely go to the CLC. The TAs there are always there and happy to help you guys. You know, the schedule is outside the door and also on Oscar. So yeah, I hope this video helped you guys. See you in the next one.